This promises to be a very exciting lecture because we'll begin by deriving what is arguably the most important formula involving prime numbers. In particular, we'll connect an endless product involving the primes with the endless sum of the reciprocals of natural numbers, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and so forth. In fact, our derivation of this formula will incorporate our previous work on geometric series. This fundamental identity, first found by the great 18th century Swiss mathematician Leonhard Euler, will lead us to a modern proof that there are infinitely many primes. We'll then see that while Euclid's ancient proof of the infinitude of primes is considered to be one of the most aesthetically appealing arguments in mathematics, Euler's analytic proof gave way to the dawn of modern analytic number theory. While we'll address the true importance of Euler's formula and its generalizations in the lecture that follows this one, here we'll explore how Euler's formula allows us to analyze subtle questions involving divisibility of generic or randomly selected natural numbers. These questions are indeed delicate and have a probabilistic feel to them. In particular, we'll determine the likelihood that a natural number selected at random will have no repeated prime factors, and through our analysis, experience for ourselves the power of Euler's remarkable formula. Leonhard Euler was an 18th century Swiss mathematician and is considered to be one of the most prolific and important mathematicians in human history. Here we introduce the celebrated formula that he discovered in 1737, which gave birth to modern analytic number theory. This formula shows that a certain product involving prime numbers equals a certain sum of fractions. It's a very strange-looking formula upon first inspection, but we'll parse it for ourselves and see exactly what it means. Euler's formula states that if we take the reciprocal of 1 minus 1/2 times the reciprocal of 1 minus 1/3 times the reciprocal of 1 minus 1/5 times the reciprocal of 1 minus 1/7 times the reciprocal of 1 minus 1/11, and so forth for each prime, then that product will equal the sum 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6, and so on. So Euler's product formula asserts that if we multiply the reciprocals of 1 minus 1 over p for every prime number p, then the result will be the sum of the reciprocals of all the natural numbers. Well, we'll now see why such a formula is believable by manipulating the product and show that it actually can be manipulated to equal the endless sum. Now, we'll treat both of these expressions as formal objects. In other words, we'll use algebra to simplify the product, but we won't wonder at this point if these expressions represent actual numbers. Well, to begin with, we'll return to our explorations into geometric series. In particular, the formula we derived for geometric infinite series. Let me remind you that if we take a ratio r that's a positive number but less than 1, then we found that the endless sum 1 plus r squared plus r cubed plus r to the fourth and so on forever actually can be summed, and we have this wonderful closed formula 1 over 1 minus r. Well, this is the key formula that will allow us to see why Euler's product formula is indeed believable. Now, for any prime number p, let's notice that its reciprocal, 1 over p, is first of all positive and less than 1. The numbers we're multiplying together in Euler's formula are of the form 1 over 1 minus 1 over p. So we now make a crucial observation. Numbers of that form are the sum of an infinite geometric series, and that's the secret. Specifically, we note that the reciprocal of 1 minus 1 over p actually equals, by our previous work, 1 plus 1 over p plus 1 over p squared plus 1 over p cubed plus 1 over p to the fourth, and so on. Well, let's now embark on a crash course in multiplication. We focus on the product in Euler's product formula, and either in a stroke of genius or madness, we'll replace each term by its equivalent infinite geometric series. So this is going to be a real mouthful here, but let's think about it together. So what we're going to do is we're going to see that if we take the reciprocal of 1 minus a half and multiply it by the reciprocal of 1 minus a third times the reciprocal of 1 minus a fifth, and we do this for every prime, then we could write that as the following product. The product that first consists of the sum 1 plus a half squared plus a half cubed plus a half to the fourth, and so on, all multiplied by the next term, which would be 1 plus a third squared plus a third cubed plus a third to the fourth, and so on, all multiplied by 1 plus a fifth squared plus a fifth cubed, and so forth down the line for all the primes. Well, to multiply these infinite geometric series together, what we do is we pluck out one term from each of the sums and multiply those terms together. We then add up all the products we get from all the different ways of plucking one term out of each of these geometric series, and that's the product. So let's take a look at some examples. If we select 1 from each series and multiply all those 1's together, we just see 1 times 1 times 1, and so we get 1. So the very first term we get when we multiply just the 1's together is the 1. Now, what if we select a half from the first series and 1's from all the others? Then when I multiply them together, I'll see a half times an infinite run of 1's that we multiply together to just get a half. Well, what if we select 1 from the first series and then a third from the second series and then 1's all from the rest? Well, then we see that product equals a third. Well, will we find a fourth in our sum? Well, yes. What we do is we select a fourth from the first series, which, by the way, notice is 1/2 squared, and we select 1's from all the rest. When I take the product, I see a fourth. What about a fifth? Sure, no problem. Select 1 from the first series, select 1 from the second series, and then pick out a fifth from the third series, and then 1's all the rest of the way, and we see a fifth. Now, how about the number a sixth? Well, the answer is yes, we'll see it, but it's a little bit trickier. Here's how we get a sixth. We pluck out a half from the first series, and then a third from the second series, and then 1's from all the rest. And that product yields 1/6. Well, because we have the reciprocals of all the powers of all the primes, then by the fundamental theorem of arithmetic that we discussed in the previous lecture, we know that this process will produce all the numbers of the form 1 over n for all natural numbers n. And by the uniqueness of the factorization, the reciprocal we see will only appear once in our sum. Let me try to illustrate this with one last example. How would we find the term 1 over 300? Well, first we factor 300. So 300 is 4 times 3 times 25. So 1 over 300 is 1/4 times 1/3 times 1/25. Therefore, we would pluck a fourth out from the first series, which is a half squared. We'd pluck the term 1/3 out from the second series, and from the third series, we'd pluck out 1/5 squared, which is 1/25, and then 1's all the rest of the way. And notice that that product is indeed 1 over 300. So we would add that in with the mix. Thus, we see that Euler's product formula, the reciprocal of 1 minus a half times the reciprocal of 1 minus a third, and so forth for all the primes, if we multiply all those together, that will equal 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, and even all the way out to plus 1 over 300 and plus and so forth forever. And now this makes sense. Kind of. Takes a while to grasp it, though. Now, As complicated as that is, I want to caution that we are not claiming that either the product on the left or the endless sum on the right represents an actual numerical value. And we'll return to this important point in just a moment. Well, applying the same reasoning as we just found, we could actually verify a slightly more general product formula that's also due to Euler. Namely, for any number, let me just call it S, he proves that the reciprocal of 1 minus 1/2 to the S power times the reciprocal of 1 minus 1 over 3 to the S power times the reciprocal of 1 minus 1/5 to the S power times the reciprocal of 1 minus 1/7 to the S, and so forth, take the product of all these primes, but now raised to the S power, then if we multiply all that out using the exact same idea, we see a sum, but now the sum is 1 plus 1/2 to the S plus 1/3 to the S plus 1/4 to the S plus 1/5 to the S plus 1/6 to the S, all the way out to 1 over 300 to the S plus, and so on, all the way out. Well, the infinite series that we just saw here, 1 plus 1/2 to the S plus 1/3 to the S plus 1/4 to the S power plus 1/5 to the S plus 1/6 to the S, and so forth, is now known as the zeta function and is written using the Greek letter zeta. We say zeta of S equals this particular infinitely long series of numbers. Well, now that we've established Euler's product formula, and by the way, that does take a while to absorb because there's lots of products that we're putting together to find the sum, we might very well ask a totally fair question: what in the world is it good for? Well, that's a wonderful, fair question. Well, first of all, the series that we saw, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 and so forth forever, is actually known as the harmonic series and is a very important object from calculus. Let's observe that each term in this sum is smaller than its predecessor, and the terms are getting arbitrarily small. In other words, the terms individually are actually shrinking down to 0. Well, this sum is important because despite the fact that the individual terms themselves are shrinking towards 0, the entire sum, taken in its entirety, is infinite. When an infinite series does not sum to a number, we say that the series diverges. Or in this case, we'd say the series diverges to infinity. Now, the harmonic series diverges, which seems counterintuitive. So we have to ask the standard question, why? Why does this infinite list of ever-shrinking numbers actually diverge, meaning that it doesn't actually sum to a number? Well, I'm going to show you an argument that verifies this, but what follows is a little bit tricky. So let's not get bogged down in the details, and if you're having fun with the details, great, and if not, let's just let it go. But here's a sneaky grouping of the terms in the harmonic series that offers us some intuition why the series actually sums to infinity, in other words, diverges. So we first collect the numbers and collect them into special groupings. So here's the grouping of the infinite series that I want us to consider. So we first start off with the 1 plus 1/2 plus 1/3 plus 1/4 and so on, and now I want to group them as follows. I want to have 1 by itself, and then I want to group 1/2 by itself. Now I'm going to pick the next two terms, which is 1/3 plus 1/4, and I want to group them together. And then I'm going to group the next 4 terms together. So 1/5 plus 1/6 plus 1/7 plus 1/8, and so on. Then I'm going to group the next 8 terms together, which would be 1/9 and so forth. And what you'll see here is I'm grouping groups of powers of 2 together. So first I have 2, then I have 4, then I'll have 8, and so forth. Now, let's take a look at the first grouping, the 1/3 plus 1/4. Notice that the fraction 1/3 is actually a larger quantity than the fraction 1/4. 1/3 is bigger than 1/4. So if we replace the 1/3 in the sum by a 1/4, we would create a smaller sum. I'd replace the bigger number 1/3 by the slightly smaller number 1/4. So now, in that first grouping, I would see a 1/4 plus 1/4. By the way, 1/4 plus 1/4 is 2/4, which equals a half. So I see now that the new sum, which is smaller, starts with 1 plus a half, and now that first grouping of terms really shrinks down to just a half. Okay, well, now let's look at the next grouping. That's the grouping of the 4 terms, 1/5 plus 1/6 plus 1/7 plus 1/8. Notice that the fractions 1/5, 1/6, 1/7 are all individually larger than the fraction 1/8. 1/8 is the smallest. Thus, if we replace those 3 fractions, 1/5, 1/6, and 1/7, each by another copy of an eighth, we would again take our sum and actually make it even smaller still. So in this case, that grouping would now be replaced by 1/8 plus 1/8 plus 1/8 plus 1/8, which equals 4/8, or, again, a half. So the next grouping of numbers actually is now a half. Interesting, we keep seeing these halves occurring. Well, in fact, this is going to be a recurring theme. If we continue this replacement process down the line, we would see that the harmonic series, the original series, is larger than the series that we're now creating, which is 1 plus a half plus a quarter plus a quarter, plus an eighth plus an eighth plus an eighth plus an eighth, plus a 16th plus a 16th plus a 16th, 8 times, and so forth. Well, this new smaller series we just created actually equals 1 plus a half plus a half plus a half plus a half forever. And since there's no end to these groupings, each of which gives a half, we see that adding infinitely many halves together yields an infinite answer. If you take a half and add it to itself forever, we're going to get something that's infinite. Thus, the larger harmonic series must be infinite as well. Hence, the harmonic series diverges to infinity. Now, that's an awful lot to grasp, but I invite you to think about it if it's something that interests you. And if not, then let's just see that we've taken the harmonic series and shown that we can produce something that seems smaller, yet is infinite. Therefore, the harmonic series must itself be infinite as well. Well, now we see why I cautioned early in our argument, as we verified Euler's formula, that it was a formal formula. The two expressions are indeed not numbers, but are equal as formal mathematical expressions. So this is a very unusual point. But using this new insight, namely the insight that the harmonic series diverges to infinity, we can apply Euler's product formula to provide a modern proof that there are infinitely many prime numbers. So even if you weren't so hot on that derivation about the divergence of the harmonic series, I want you to come back here because this is really neat. This is really, really neat. So we're going to now prove that there are infinitely many primes, but using this formula. Now, this proof is by contradiction, which means that we'll assume that there are only finitely many prime numbers, and we'll argue that this assumption leads to a contradiction. In other words, a logical fallacy. Well, if there were only finitely many prime numbers, then the product in Euler's formula, remember that product on the left, the reciprocal of 1 minus a half times the reciprocal of 1 minus a third times the reciprocal of 1 minus a fifth, and so on? Well, there would be a last factor in that product. Thus, we'd have a product of a finite number of rational numbers, a finite number of fractions. And that product would be another fraction. However, by Euler's product formula, we know that this product equals the harmonic series, which we just demonstrated equals infinity. Therefore, we are forced to conclude that there is a rational number, a ratio of two natural numbers, that equals infinity. Well, this is obviously impossible, and thus we've reached a contradiction. This fallacy implies that our original assumption must have been false. Hence, there must be, in fact, infinitely many primes. Well, notice how different this argument is from Euclid's original proof that there are infinitely many primes. Absolutely wonderful. This formula actually gives us some information about the primes, albeit information that we already knew from ancient Greek mathematics. Euler's general product formula has important implications actually in the study of primes, and I want to illustrate one of these implications right now. But to begin with, I want to consider a very, very simple question and then slowly build up. Suppose we randomly pick a natural number. What is the probability that this number is odd? Well, to answer this question, we consider the opposite question. What is the probability that this number is even? Well, a number is even precisely when it's a multiple of 2. We've already seen this. Well, since every other number is a multiple of 2, the probability that the number is even equals 1/2. Well, to find the probability of the opposite scenario, the opposite probability, we compute 1 minus 1/2, which still equals 1/2. So we conclude that the probability that the random number is odd equals 1/2, which maybe is not so startling. Maybe that intuitively made sense to you. But I wanted us to think about the reasoning in this way because we're going to see this reasoning actually allows us to do something else. In fact, this elementary analysis can be extended to answer a much more interesting and subtle number theory question. Moving beyond the prime numbers, those numbers that have just one number appearing in their prime factorization, we now consider those numbers whose prime factorizations consist of no repeated primes. That is, those numbers for which the primes appearing in its prime factorizations appear only once. These numbers are called square-free, and in some sense produce the next level of generality after the primes, namely the numbers that just have the primes multiples appearing just once. For example, 6 is square-free because no repeated primes appear in its factorization. We just see 2 times 3, both primes appear once. However, 20 is not square-free because it does have a repeated factor in its prime factorization. Notice that 20 equals 2 times 2 times 5, and we see a repeated factor. Similarly, a number like 54 is not square-free because if we factor 54, we'd see 2 times 3 times 3 times 3. So we see the repeated factor of 3, and therefore it's not square-free. If we pick a number at random, a natural number at random, what is the probability that it's square-free? In other words, what's the probability that it's not a multiple of 2 squared, not a multiple of 3 squared, not a multiple of 5 squared, not a multiple of 7 squared, not a multiple of 11 squared, and so forth down the line for each and every prime number? Well, applying our method for answering the easy question of a number not being a multiple of 2, we see that the likelihood of not being a multiple of 2 squared equals 1 minus 1/2 squared. The likelihood of not being a multiple of 3 squared equals 1 minus 1 over 3 squared, or 1 minus 1/3 squared. And in general, for any prime number p, the likelihood that a random natural number is not a multiple of p squared equals 1 minus 1 over p squared. Well, we'll find our answer by multiplying all these individual probabilities together. Now let's pause for a moment to see why multiplying these probabilities makes sense. Suppose we flip a fair coin. What's the probability of seeing tails? Well, it's 1/2 because there's 2 possibilities, heads, tails, and they're equally likely, so 1 out of 2. Well, what if we flip the coin twice? Well, now the coin has no memory, so it doesn't know how it landed one way and doesn't know how it's going to land the next way. So there's no memory, it doesn't record what it's done. So the probability that we see 2 tails in a row would actually be 1/2 multiplied by 1/2, which would be 1/4. And in fact, the probability of flipping a coin twice and seeing a tail followed by a tail is in fact 1 out of 4. Similarly, returning to our square-free probabilities, we string all our probabilities together with multiplication, as if we were flipping a coin again and again and again. In other words, we'll view the likelihood with respect to each prime as independent. So the probability of having no prime appearing twice is the product 1 minus 1 over 2 squared times 1 minus 1 over 3 squared times 1 minus 1 over 5 squared times 1 minus 1 over 7 squared, and so forth. We do this for each prime. Notice that this product is in fact the reciprocal of the product from Euler's general product formula with S equals 2. Therefore, this product equals, by the product formula, the reciprocal of the sum of the squares of all the natural numbers. In particular, the product equals the reciprocal of 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared plus 1/5 squared plus 1/6 squared plus 1/7 squared, and so forth, the reciprocal of the square of every natural number. And this number can actually be written as 1 over zeta of 2, because remember, we use the zeta symbol to represent this sum, and since we're letting the exponent be 2, we see this as 1 over zeta of 2. Well, unlike the harmonic series that we saw earlier, here the terms from the infinite series zeta of 2 do shrink to 0 fast enough so that the entire infinite series does converge upon a number, just like we saw with the geometric infinite series. Now, this infinite series can be computed precisely using some advanced mathematical ideas from calculus. But let me just tell you that the answer is zeta of 2, that infinite series, equals pi squared divided by 6. Remember that pi, which we saw from geometry way back in our school days, is equal to around 3.1415 and so forth. So we're looking at that number squared divided by 6. Well, returning to our question, we see that the probability that a random natural number is square-free is actually the reciprocal of zeta of 2, which is the reciprocal of pi squared over 6, namely 6 over pi squared. We can use a calculator to see what this number looks like in decimal form, and we see it's 0.6079, and it goes on, or approximately a probability of 61%. Well, this is amazing, because what we're saying is that if you pick a number out at random, it's more likely than not, in fact, approaching 2/3 chance that it's going to be square-free. So the square-free numbers seem to be more popular within the natural numbers than the numbers that are not square-free. So a new insight. Now we can actually try an example to see if this number is at least reasonable or believable. We could actually count how many numbers less than or equal to 100 are square-free. So let's just consider picking a random number from 1 to 100. Forget about picking a random number from 1 to forever. Now, you can actually use a sieve type method that we saw in the previous lecture, and we could actually see how many of these square-free numbers there are. In fact, if you try the sieve method on your own, you need only cross off the multiples of 4, 9, 25, and 49. And I'll let you think about that. But if we did this, and I did this already, we discovered that there are, in fact, 61 square-free numbers from the first 100 natural numbers. So, the probability of picking a square-free number out of the first 100 natural numbers is 61 out of 100, or 0.61, or 61%, which is amazingly close to the actual value we computed when we pick among any natural number of 60.79%, which we just found. So, it is more likely than not that a natural number picked at random will have no repeated factors. Absolutely amazing that we could find that out. We've just made a new insight into the infinite collection of natural numbers. Even though we can't say things about all of the numbers taken, at large, we don't know all those big prime numbers, we can say something precise about the totality if we pick a number out at random. Euler's product formula not only provides important insights into the prime numbers, but actually appears in unexpected places throughout mathematics and science. In the next lecture, we'll see how Euler's formula leads to one of the most famous, long-standing open questions in all of mathematics. Euler himself wondered about a pattern within the primes. His words today still ring true. He wrote, "Mathematicians have tried in vain to this day to discover some order in the sequence of prime numbers, and we have reason to believe that it is a mystery into which the mind will never penetrate." So we see that the study of primes is indeed an enormous challenge, and the next lecture will see some open questions that still tantalize practitioners of number theory to this very day and into the future.